Hello everyone. This video covers sections 18.1 and 18.2. All of chapter 18 is about stochastic calculus, and this could be something that you may have never seen before, which is okay. That's why we're doing this right now. Just like Brownian motion, many of you may have not seen it before, but you saw that it's not that bad. Now, the name tells you exactly what we're going to do, calculus, but this is a slightly different calculus. So remember the regular calculus that you did in, calculus 1, calculus 2, and calculus 3. There's technically two things that you do in calculus only. You either take derivatives or you integrate. That's pretty much what you do in calculus 1, calculus 2, and calculus 3. Well, in stochastic calculus, we're going to do pretty much the same thing, derivatives. We're also going to integrate. And all the rules and properties from calculus, regular calculus, are still going to apply, but there will be some differences. That's why this has a different name. And that's what we're going to learn in 18.1 and 18.2. Also, this should be obvious, but just to refresh your memory, remember that if you take the derivative, say with respect to x of x cubed, the derivative is 3x squared. Also, if this is the case, remember that the integral of 3x squared dx, should be equals to x cubed plus some constant. So the point is that these two are the inverse of each other depending on the functions we have. This is going to be very important also for what we do right now. So if you can do this, you should be able to get this, and the other way around. Now, before we define the Ito integral, remember that since the main idea of this class is pricing, and you want to know what happens to the stack price, we usually go from 0, which is right now, to capital T, which is sometimes called just Tn. Okay. So therefore, if we discretize this, you have the following sequence: 0 less than equals to T0, less than T1, less than T2, and so forth, until you get to less than or equals to Tn, which is the last one. And pretty much you increase by delta T every single time, just like we have done a few times already. Now, before we go to the actual E2 integral, let me remind you again from something from calculus 1. Recall from calculus 1, at the very beginning of when you do integrals, which I believe is in chapter 5, remember that the integral from a to b of f of x dx is defined to be the limit as n goes to infinity of the Riemann sums, which in this case is the sum from I equals to 0 to n of f of x I delta x. Remember that this is the same thing as saying as delta x goes to 0. So this was the actual definition of integral before. Now, if you compare the Riemann integral, remember this was the Riemann integral, you compare that with the E2 integral, which is this one right here, the first thing you should notice is that this function and this function could be the same type of function, which is a non-random function. But here we're integrating with respect to x, which x is not a random variable. Well, here, this one is with respect to Brownian motion, or the Wiener process. So this is a Brownian motion. Remember that Brownian motion was a stochastic process that is continuous everywhere. but is differentiable nowhere, so the derivative doesn't exist at any point. So therefore here, if you notice, for the limit, I actually have some dots in between, and the reason for that is to emphasize that when we say limit, even though this, you can see, looks exactly like this limit is very different than this limit. When we say a limit in a stochastic process, for especially for this case, we are taking the limit or convergence in something that is called mean square error convergence. So still going to converge to the integral, but the convergence in this case is very different than this. So what do we mean by mean square convergence? Well, that means the following: that the expected value of the integral or the E2 integral, you subtract the approximation or the sums from I equals to 0 to n minus 1 of h of ti times the Brownian motion or the Wiener process. You do the square of this expected value, that this goes to 0 as delta goes to 0. So that's what I mean by mean square error convergence, where delta is equals to the maximum of the intervals. This is ti plus 1 minus ti. Remember, this is what we define to be delta t. And here, h of t is a continuous function. So it has to be continuous and bounded. It actually works for some non-bounded functions, but those are specific cases. So therefore, if you can compute this and take the limit in this sense, this will be the definition of the E2 integral. All right, then the E2 integral has the following properties, which we'll get into more detail later. I think some of them are asking the homework questions to show that this is the case. But the first property is this: if you take the expected value, which is the same expected value here, or the E2 integral, this is equals to, it's going to be equals to 0. The second property is that you take the E2 integral of, you take the expected value of the integral square. This is the same thing as just doing the integral of the regular function with h of t. Notice how the dwt is transformed into a regular integral. So this is a pretty interesting property, because if you take the expected value of the integral square, it's the same thing as just doing the regular integral of the function of the expected value square. Now, just like in calculus 1, when you learn how to find integrals, the first thing you do is you find the integral using this definition, which, if you remember, it took a long time. But then there are some rules that will make taking integrals a lot easier. So first, we're going to do an integral the long way using this definition. Then after that, there is a kind of a faster way to do the integrals. So in this example, it's asking you to find the integral from 0 to t of the Wiener process with respect to the Wiener process. Again, this is not a regular integral because you're integrating with respect to a random variable, not a regular variable. Remember here that t goes between t0 all the way to tn. Okay. So then if we use the definition that we just have right now, this part is going to be in summation form, the sum from I equals to 0 to n minus 1 WTI. In this case, this is h of ti. Remember, h can be random or non-random. And then this part, the dwt, remember, is wti plus 1 minus wti. Now, don't forget what we did before. Remember that this is still a normal distribution that has a mean 0, but a mean 0, but a variance of this minus that. Right now, we're gonna do the same trick we did before, which was to add nothing. But before we do that, notice that this is the same thing, okay, as the sum of WTI times WTI plus 1 you distribute minus WTI squared. So that's what you have so far. Okay. Now we're gonna do the usual trick of adding nothing. So this is gonna be the sum from I equals to 0 to n minus 1. Now we're gonna add nothing to it. So nothing we're gonna add is gonna be 1/2 WTI plus 1 squared minus 1/2 W squared TI. Remember, this is equals to 0, and you still have here the plus WTI plus 1 minus WTI squared. Okay. Notice that this you can rewrite it as minus 1/2 WTI squared minus 1/2 WTI squared. Okay, because minus 1/2 minus 1/2 is minus 1. So then if you combine this part with one of this, then you will get the following. This will be the sum from I equals to 0 n minus 1 1/2 W squared TI plus 1 minus WTI squared. So if you combine the two in green, you end up with this part. Now, if you combine the three terms that are left, which is this one, and this one, so we'll get the following. You can factor the minus 1/2. This will be W squared TI plus 1. Then this has to be minus 2. Why? Because minus 2 over 2 gives you 1. So this is just basic factoring from algebra. This will be WTI times WTI plus 1. And then finally this will be plus, because minus and minus is going to be plus WTI squared. Okay, so all the yellow part will give you all of this. And remember that all of this is inside the sum. So all of this is inside. Now notice that all of this is exactly the same thing as WTI plus 1. That's just basic algebra again. minus WTI, the whole thing squared. Hence, we get the following. This is the sum for I equals to 0 to n minus 1 of 1/2 WTI plus 1 square minus WTI square minus 1/2 the sum, if you break it into two pieces, I equals to 0 to n minus 1 of WTI plus 1 minus WTI, the whole thing squared. Notice that if you expand the first sum, this one in here, when I is 0, you will have W of T1 minus W of T0, which remember this is equals to 0, and then plus W of T2 minus W of T1, and so forth until you get to the very last one, which will be W of Tn. But remember, Tn is nothing more than just W of T. Here, the key is that you can see that this will cancel with this. All of them will cancel except for this one in the beginning. So therefore, the first part, this is just going to be 1/2 capital T. For the second part, notice that W Ti plus 1 minus W Ti. Remember that this is a normal distribution with mean 0, and the variance is Ti plus 1 minus Ti, which remember this was nothing more than delta T. Therefore, if we take the limit in the mean square sense, then from here we have the following, that the integral or the Ito integral or stochastic integral with respect to a linear motion by definition is going to be equals to the limit as delta goes to 0 of all of this, the first part and then the second part. Well, we already know that the second part is equals to just 1/2 W capital T squared, and the second part is going to be 1/2 times T. Well, how do we get T? Remember that from here the expected value of W T plus 1 minus W T I squared was equals to Ti plus 1 minus Ti, which was just delta T. And if you do the sum of all the delta T's, which is what you have to do here, you end up with T. As you can see, using the definition is a pretty long and lengthy process, but very soon we'll see a faster way to do this, where you can find the integrals without using the definition. But everybody needs to see this at least once, because this is how the integral is actually defined. Notice that if this was just a regular integral, okay, from the past, if you're just integrating x dx, the integral is equals to 1/2 x squared, and that's it. Here, notice how you have an extra term which you didn't have before. The reason why we want to have this extra term is because the quadratic variation for the Wiener process is not equals to 0. Remember, the quadratic variation was equals to this part, and clearly that's not equals to 0, so that's how we end up with this part right here. Don't forget that also the way how we got this was taking the limit, but the limit was in the expected value form, not the typical limit. Like I said before, there is a connection between taking a derivative and taking an integral. We're going to see next is actually a formula that can take derivatives of stochastic processes, and to find integrals you will see that it's actually easier to take the derivative of the function that you want to get the integral to, and then you just rewrite the problem. In essence, what we're going to do in the next page, which is called Ito's formula, is the following. Remember, you wanted to find the integral of x squared dx. Well, the integral is 1/3 x cubed, which should be obvious, should be pretty easy. So Ito's formula, it will be actually easier to take the derivative with respect to x of 1/3. The derivative of this is x squared, and that's going to imply that the integral of x squared dx is equals to 1/3 x cubed plus some constant. So this is kind of what Ito's formula does. So if you want this, you pretty much take the derivative of the function that you think it will give you the integral, and then you rewrite it. Obviously, it's going to be a little more involved, but this is pretty much the basic idea. Ito's formula is one of the most important formulas in stochastic processes, or specifically for stochastic calculus, because it's how you're going to be able to take derivatives of stochastic processes. Remember that the Brownian motion is not differentiable anywhere, but this one, or this formula, will allow you to still take derivatives in the stochastic sense. So this is how you do this. So you want to have a process yt, which is going to be some function. This is a non-random function. The function is going to depend on t and some random process. So this is some random process, okay? Where the random process is going to have the following derivative. This is actually called a stochastic differential equation, okay? And this is specific to whatever process you have. Notice here, Brownian motion is actually what's giving this process the randomness, and mu is a function that could depend on both of them, but most of the problems we will do, mu and sigma are usually just constants. So stochastic differential equations of this type, they are usually just called SDE for a stochastic differential equation. And when you take the derivative of this, so you have to use partial derivatives because you technically have two variables here. So dy dt is going to be the derivative. Notice how you can just divide everything on this side, and this is definitely another stochastic differential equation. So this is actually pretty easy. You just have to be very careful to know which functions you have. So this is what the formula says. If you want to take the derivative of this in the stochastic sense, this is what you do. You need to have a function g. You're going to do the partial derivative of g with respect to t. Notice that there is a short way to write this. This is also just g with respect to t. Then the dt goes here, so this is very important. Then you do the derivative of g with respect to x, which again you can write it like this. And you're going to multiply this times dxt, which this is unique to whatever problem you have. So in our particular case, dx dt is all of this right here. And then finally, you're going to have the second derivative, which will be gxx, you use the notation, times dx dt. Remember that dx dt, this is exactly all of this is square. and there is a 1/2 missing in front. By the way, you can get this formula using a Taylor expansion. You don't actually need to know how to do that, but this formula comes from using a Taylor series. Again, this part is here because the quadratic variation is not equals to 0, so this is still part of the problem. So you could say that this is the part that is new, that you never seen before. All of this is the part that is new. The 1/2, remember, goes in front. Now, to make our life easier, there is something that you just need to remember. For now, you just have to take it as given. If you do dt times dt, it's going to be the same thing as dt times dwt, the same thing as dwt times dt, and this is always going to be equals to 0. And if you do dwt times dwt, this is always going to be equals to dt. So this is very important, so you should just memorize this. All right, so let's do an example. Here xt is going to be the process, which is just pretty much the winner process. Notice here the if you do the dx dt, this is technically just dw dt, I mean dwt. This process doesn't have anything in front, only has the second part. So this is the most basic one, so the x dt is equals to this. Actually, probably would make more sense to write it this way. The x dt, it will be equals to 0 dt plus dwt. Okay. So this always has to be given, otherwise you won't be able to do the problem. Here, notice that you're pretty much trying to find this. Y of t is equals to 1/2 wt squared or x squared. Therefore, the function we have, the g function, which is also crucial to this, is just equals to 1/2 x squared. Now, since g doesn't depend on t, therefore the partial derivative of g with respect to t, or is going to be 0. Then the partial derivative of g with respect to x is going to be just x, and then the second derivative of g with respect to x is going to be 1. You should do all of this on the side first, because you're going to need all of this on the formula. You can say here the g dt, the g dx, then the second derivative. Once you have this and you know what the x dt, all you have to do is literally plug it into the formula. So this is what we have. dy t is going to be equals to dg dt, which is 0 times dt. Okay, remember this dt is going to be this dt plus dg dx, which in our case is x, but remember x is the same thing as the Brownian motion or the winner process, so this will be wt dwt. Why? Because the x is just equals to dwt, because there is nothing here, and then plus 1/2 the second derivative, which was equals to 1. And then remember, if dt, if dx dt is just equals to dw dt, therefore, based on this rule, that means that dx t squared is the same thing as just dwt squared, which again is not always the case, but for this case it is. So this is just equals to dt. So therefore this will be dt from here. Then you just combine all the dt. This one is 0, there's no need to combine. So therefore this will be 1/2 dt plus wt dwt. And that's the derivative. Now notice the following, and this is very, very important. Remember that dy dt is the same thing as this. This is technically the derivative of 1/2 wt squared, because that was the definition of this. And we got that this was equals to wt dwt plus 1/2 dt. Okay. Now remember from calculus 1, from regular calculus, if you want to get rid of the derivative, which is this, you just integrate. So therefore, if you integrate both sides, on the left side you'll have 1/2 wt squared. On the right side, this is going to be the integral from 0 to t wt dwt plus 1/2 dt. Remember the integral of dt is just t. So from here you can see that the integral from 0 to t of wt dwt is going to be equals to 1/2 wt squared minus, this is just 1/2 times t. You go from 0 to t, 1/2 t, which is exactly the same result we got in the previous page, but you don't have to go through any sums or anything like that. So this will be an easier way to know what this integral was. Again, this is very, very important, so take a close look to this, stop the video and really check this. We're gonna do 2 more examples on this, but this is very important so you can see that you get the exact same answer using just Ito's formula instead of going through the definition of the Ito's integral. All right, let's try one more example. Here, y of t is equals to 2 plus t e to the wt. Notice that the stochastic process again is just the Wiener process. So in our case, xt, just like the previous example, is equals to wt, which again is not always the case. So for this particular example, the x dt is just the wt. Okay. Now let me write the formula again. Remember, Ito's formula says the following: that dy dt is going to be equals to the partial of g with respect to t of t xt dt plus the partial of g with respect to x dxt, and then finally plus 1/2 the partial of g with respect to x, and then this will be t xt, the whole thing dxt squared. Okay, so it's just the same formula and just rewriting it. So this should be dxt squared. Now here the function g of t and x is equals to 2 plus t plus e to the x. All right, so we need to take the partial derivatives just like in the previous example. So the derivative of g with respect to t will be 1 in this case. The derivative of g with respect to x, it will be just e to the x. and the second derivative of g with respect to x is also going to be just e to the x. So therefore, if we plug it into the formula, we will get that dyt is equals to 1 times dt. Remember that this dt is this one right here, plus dg dx, which is equals to e to the x. But remember, x here stands for the Wiener process, so this will be e to the wt times dwt plus 1/2. The second derivative was also e to the wt times dwt square, which, remember, this is always going to be just dt. So therefore, you end up with dt plus e to the wt dwt plus 1/2 e to the wt times dt. We have dt here and dt here, so you can factor out the dt. So you'll get 1 plus 1/2 e to the wt, the whole thing dt, plus e to the wt dwt. So again, you can see this is not hard at all. Just make sure you follow the formula, correctly identify which function is g, and also make sure that you know what the x dt is. In the previous two examples, the x dt was just equals to dw dt because the process was just the Brownian motion, or the Wiener process. In the next example, that's not the case, so it's a little more tricky. All right, let's do one more example. So this is the formula for the geometric Brownian motion. Here, the value for g, or the function g, is equals to s0 e to the mu t plus sigma x. All right, so we need to find the partial derivative. So the derivative of g with respect to t is the same thing as s0 e to the mu t plus sigma x times mu by the chain rule. But remember, all of this is just equals to g by definition. So therefore, this is just equals to mu times g. Remember here, g is a function of t and x, or a function of t and the Brownian motion. Right, so doing the same thing again, the partial derivative of g with respect to x is going to be, again, s0 e to the mu t plus sigma x times the derivative with respect to x, which is just going to be sigma. And by the same logic as this one, you'll end up with sigma g. We also need a second derivative of g with respect to x. And remember, the second derivative is the derivative of this again, so this will give us s0 e to the mu t plus sigma x. We already have sigma here, so you're going to multiply times another sigma. So this is going to be g square, sigma square times g. All right, so now if we apply Ito's formula, which is the same formula we used twice already, we get the following: d of st is going to be equals to g mu dt plus sigma g dwt plus 1/2 sigma square g dt. Now notice that g is the same thing as just s of t on our particular example. So therefore this should be s of t mu dt plus s of t sigma dwt plus 1/2 sigma square s of t dt. Finally, you can combine the dt like we have done in the previous examples. So then if we do that, this will be mu plus 1/2 sigma square s of t dt plus sigma s of t dwt. And again, this is technically just a stochastic differential equation. So it's a stochastic differential equation where the initial condition is equals to S0, which in our case, this is the initial price or the initial value of the stock. You can rewrite the equation like this if you want to. It's not really necessary unless the question is asking you to do this. You can divide everything by dt. So this looks more like a calculus derivative. And then this will be mu plus 1/2 sigma square s of t plus sigma s of t dw dot t, where this is just the derivative of the Brownian motion with respect to t.